All right, so we're going to go ahead now and take a look at this starting definition for what this section 4.7 is going to be all about. So this definition is really the heart of this section. A transformation from the UV plane to the XY plane is a function of the following form. Okay, so already this can look a little bit intimidating, but just notice that what we're introducing here is a UV plane. It's kind of like how with a regular substitution we introduced a new variable of u, but now since we're working in an xy plane, we have to kind of introduce two new variables. We have to take a region in the xy plane that I might be integrating over, so maybe this is a region up here in x's and y's, and maybe it's a really difficult region to integrate over, right? Maybe it's some weird shape. And what I'd like to do is to imagine a way that I could modify that and morph it in some way, maybe into a nice easy region in a new plane called the UV plane. Kind of like how we had to adjust our intervals again when we did a U substitution. Our goal is to take something difficult to integrate over and maybe modify it into something simple. And this idea of a transformation is what's going to make this happen. So we're going to take something from the UV plane and move it to the XY plane. So in my picture here, I'm actually going to have a slight modification in that I'm going to create things that can go like this. And this arrow is some sort of a function that can kind of map points from this UV plane over into the XY. It can kind of tell you where every point over here ends up over there. Okay. So this is how the function works. You can see it's a function t and it has two inputs. And the inputs are u and v. So let's plug in a point from over in this space. And what it will spit out is, well, a new point. Some formula will take in the u's and v's and spit out a first coordinate. Some formula will take in u's and v's and spit out another coordinate. And so as I state here, we kind of think about this g of uv as spitting out an x value, and this guy here, the hu of v, spitting out a y value. So if I plug in a u comma v, I can kind of map it over. Maybe like this uv over here maps to this x comma y over in the other picture. So this is the idea of what a transformation is. And we're going to see how we can use that here in a couple different ways. So we'll identify here two other definitions. A transformation of the form, again, takes a u and a v and spits out, again, an x and a y. We'll call that a C1 transformation if the functions g and h have continuous first-order partials. So again, keep in mind that if g and h are definitely functions with two variables, we can find partial derivatives of them like we did back when we talked about partial derivatives much earlier in this course. Okay. We can also say here that if I have a t, again, keep in mind here it's taking in the values of a u and a v, and it's spitting out the values of an x and a y. And we can say that CD is the image of the point AB. It's kind of what AB gets transformed into. It's the image under that transformation. If no two points have the same image, that is, if there's only one UV that can ever produce x comma y, then we can call that transformation a one-to-one transformation. Every time you plug something in, you get something unique out. There's never going to be any other input that could produce the same output. So we're going to go ahead and try to mess around with these definitions and some transformations like I have here. So let's take a look at this transformation. We won't think about what regions in the XY plane and the UV plane we're working with just yet. Let's just try to focus on how this thing works. Okay, so here's a transformation. I can see that, again, there's going to be a u and a v that are inputted, and then there's a formula to help me compute the corresponding x and the corresponding y that I would get back. So one of the questions that I might have here is this a C1 transformation? Well, that, of course, should be really, really easy to see, because I can recognize that my g of uv, remember, this produces my x's, that's just u plus v. And I can see that h of uv, that's the formula that produces my y's. And I can say, do these have continuous first-order partials? And I can say both the G and the H have continuous first order partials. That's almost pretty easy to spot just by the functions themselves, because they are both polynomial functions, and so their derivatives are going to be polynomials, and all polynomials are going to be continuous. So we can then claim T is a C1 transformation. Okay, so this is at least what the definition up here is kind of demanding, that I meet these criteria. And so here I have a special kind of transformation. It meets this criteria to be a C1 transformation. I could then ask the following question. What is the image of 2, 3 under T? So notice that this is saying that if I have a U and a V point right here, and I want to transform those with T into an X and a Y, what is it that I get? Well, again, that's super easy to do because I already have the formula up there. If I take T and I plug in a 2, 3, I know that what I'm getting back, according to the formula up above, is a 2 plus a 3, comma, a 3 squared. And that, of course, is the same as a 5, 9, and I should keep in mind that this is now an X, Y point. So I took a U, V, and I made an X, Y. So that's pretty straightforward as well. Oh, sorry, it looks like I made a small typo here. This is supposed to be 3 to the 3rd power, and so of course it's not 9, but that would be 27. Okay, so I could then ask the question, is this a one-to-one transformation? Remember, in order to be a one-to-one transformation, I have to say that no two inputs, no 2 points A, B, could ever produce the same exact result. So I could kind of ask the question here, like, could any other point besides 2, 3 make the point 5, 27? Now, that might be kind of hard to determine maybe at first, and even if I was able to say no to that, that doesn't mean that there's no other 2 points out there in the world that could make a similar output, even if it happens to be different from this guy. Maybe there are 2 points out here that can make 1, 1 pop out. So if I'm oftentimes testing for a one-to-one transformation, I can write an argument kind of like the following. I can say, let's assume T is not a one-to-one transformation. And I'm going to do this in order to try to maybe reach a contradiction. I'm going to assume that no is the right answer here, and then I'll see if that causes any problems. So if I assume that this is not a transformation, then I'll also say here that we can start to play around with maybe 2 different points. So assume 2 different points, let's say A, B, and C, D, have the same image under T. So those are U, V points, and I'm going to plug them into the T formula, and I'm going to suppose, well, if it's not one-to-one, then there's got to be 2 points out there that make the same result. Okay? So what we really mean here is that when I go and I plug A, B in, that means I'm saying that I get the exact same thing when I plug C, D in. Let's just pretend this is the case because we said this is not a one-to-one transformation. Of course, that implies a couple things. If those 2 points are the same, then doesn't that have to mean that when I use this transformation, which said take the U and the V value and add them together and take the V and cube it, well, that would mean that A plus B, comma B cubed, must be identical to C plus D, D comma cubed. Or sorry, comma D cubed, right? Like these 2 points then would have to be the same because these would be the X, Y's that result. But of course, I could then see that the only way these 2 points could be the same is if B cubed and D cubed ended up being the same number, right? Like, I mean, if these things don't have the same Y component, how could they be the same? But of course, if these things are going to be the same, there's no option except to let B and D actually be the same number. So if that's the case, then I could also say that I know that A plus B has to be equal to C plus D if these things are going to match. But since since B and D are the same number that we established up above, I could really say that A plus B is really equal to C plus B. But then if I subtract B from both sides, I'm going to get that A is equal to C. So if I look at the statements that I've come across here, I've kind of said, if you give me 2 points with the same outputs, then automatically we've kind of found these points are actually the same. A comma B is equal to C comma D. But this is a contradiction because we said that these should have been 2 different points. So I'll say this is a contradiction, so T must be 1-to-1. That's the only other option. I can't have it be not 1-to-1 because anytime I claim that I get 2 different points producing the same output, they end up being the same point anyways. Okay, so this is kind of a whole bunch of different definitions here that we have, and we'll come back to these definitions in a later video. They do become very important in this section. For the moment, they'll slightly disappear, but they'll reemerge when we introduce our formula a couple videos from now. Okay, in the next video, we'll take a look at example 2 to try to start to see how I could use a transformation not only to shift around points, but to shift around entire regions, and how I could identify like a region D and a region S, kind of like what we talked about in the opening video.